I would like to welcome Steve Hipskin, and he's the chief of the Earth Sciences Division at NASA Ames Research Center. He specially came down to talk to you at the last minute, so I'm really glad that he's here to give us our closing speech here. Anyway, the division is primarily a research group, and it's working on global to local problems in earth sciences using NASA's unique perspective from space. The division focuses on atmosphere and ecosystem science and technology and development. It comprises over 100 scientists, a lot of engineers, technical support personnel. And at any rate, I want to welcome Steve.
Well, thank you very much, Catherine and Ed and all of the IEEE organizers of the meeting. Appreciate the opportunity to come here and talk to you about the cool stuff that we do up the road at NASA Ames, which is at Moffett Field. I would argue that most people, when they think of the space agency, still think primarily of the human spaceflight program. And so I'm going to talk to you today about the observations that we make from space of our home planet. And we actually have a program within, NASA is primarily a research agency, but we do have a program within NASA called the Applied Science Program, which really looks for making the connections. NASA is not an operational agency, so as John said, actually we look for the connections with the operational agencies, organizations, to try to utilize the data that we glean from space.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Have ignition and liftoff of the Atlas V rocket on the Landsat Data Continuity Mission, continuing the 40-year legacy of preserving Earth's natural resources from space.
So that's some of the kind of fun stuff we get to be part of. One of the interesting things about that is it talks to the partnerships that NASA has. And so in addition to the science-oriented missions that we operate, we also work very closely with operational agencies. In this case, the USGS has the responsibility for land imaging. So NASA builds the Landsat series of satellites. They're actually one of the best examples of the importance of time rate of change. Landsat is a 40-year program, and so we have 40 years of those observations of the Earth from space. We also work with NOAA, the National Oceanic and Atmospheric Administration, and we basically build and launch the weather satellites, and once we certify that they're actually working, we turn them over to NOAA for operations. So I think this image has been used a lot, but this is the Christmas Eve image of the Earth as seen from the first Apollo 8 mission, which was the mission that just went around the moon without landing. But in a lot of ways, this image really demonstrated the value and importance of being able to see our home planet from outside of our planet. And it really spurred the effort to see what we could do from space. And so we went from that start in the late 60s to more recently. This is the current constellation of NASA satellites. There are 17 operating satellites, so all of the ones in blue and on the lower part. Looking at just the whole suite, NASA's focused modestly is Earth system science. So we really are the agency that has the global perspective, and we really try to make the connections of all of the Earth systems, from the oceans to the atmospheres, land, ecosystems, the whole gamut. And with any luck, this is just a different view of that constellation. What you can see, this is the orbits of those satellites that I just showed you. If you kind of take a look at it for a little while, you see that many of them orbit over the poles. That's typical for Earth observation missions, where you you orbit the pole. As the Earth rotates underneath your orbit, you're able to image the entire planet. And if you look even closer, it looks a little jumpy. I think my computer's struggling with its all the stuff I have on it. You see that there are several of them that are together. That's actually our first effort at doing an actual formation flight. We actually call it the A-train. And so you really magnify the power of those different satellite instruments by putting them in very close proximity to one another so that you're getting multiple images of the Earth from different instruments. This year is a big year for NASA Earth Science. We actually have all of these different instruments that actually have or are being launched in this year. So this is actually a first for us for many years, but it speaks to the strength of our the longevity of the Earth Science program at NASA, and so we've already launched three of these this year already. So GPM is the Global Precipitation Mission. It's a partnership with JAXA, which is the Japanese Space Agency. But it's the satellite that basically looks at precipitation over the whole globe, which is extremely important, as you might imagine, in understanding climate change, impacts of climate change on precipitation. And so, you know, until we started measuring precipitation from satellite, you know, really the only precipitation measurements were those on land. And so 2/3 of the planet is actually ocean. And so it's the observations of space that give us those measurements. OCO2 is our first effort to actually measure columns of atmospheric CO2 from space. That was launched just a few months ago. And indeed, the most recent launch was RapidScat, which is basically a scatterometer that's looking at surface winds of the ocean. And that actually went up with the most recent SpaceX launch up to the International Space Station. And it's going to be making the measurements from the International Space Station. And then coming later this year, CATS is a cloud aerosol instrument also going to the space station. And SMAP, which is soil moisture, active and passive, which again, we have a suite of instruments that look at the hydrological cycle, and having the soil moisture over the globe is an important part of that constellation. In addition to that those images from space, NASA really, I mean, it's way much more than the observations that we take, but it's really a scientific program with scientists at the agency around. We have 10 different NASA centers around the country, but we also work very closely with our partners at other agencies, academia, private industry. And so we fill in the measurements from space with measurements from aircraft. We actually have surface stations. And so we have a wide range of the kind of measurements that we need. The aircraft program, it has several uses. One of the most important for us is that when you launch these satellites, you really have to understand how your retrieval algorithms are working, because you're really just looking at retrievals in the electromagnetic spectrum. And so you need to verify with ground measurements or airborne measurements that your algorithms for those retrievals are working correctly. But we also use them for doing detailed process studies. A lot of time with the global view from space, you can't see the very detailed microphysical processes in clouds, for example, or photochemical processes. So for example, we for many years and continue to use the ER-2, basically the civilian version of the U-2 aircraft. And it was actually that aircraft that we used in the late 80s to look at the ozone hole and return the smoking gun that showed indeed we had already had the measurements from space but didn't understand the processes behind that. And we returned the smoking gun that pointed to the man-made CFCs. We at NASA Ames are also looking at smaller robotic aircraft. These are some of the aircraft that we're flying. We actually built up the one that you see in the upper left. First mission that we ever did was to Kiruna, which is probably some of the most difficult environment that you could actually fly one of these in. We were looking at surface ice roughness. And then more recently, we're looking at these very small Dragon Eye aircraft, and we took those down to Costa Rica to make SO2 measurements over volcanoes. So perfect example of a place where you wouldn't particularly want to put a pilot in harm's way. And so these robotic aircraft are demonstrating that we can get measurements where you otherwise couldn't or wouldn't want to. In fact, the week after we were down there at Turrialba, the volcano outgassed, and so luckily we had already left before it took out one of our aircraft. And then finally, one of the things that we're very interested in up at NASA Ames is really making measurements for much smaller aircraft. This image actually looks like a cartoon, but it's actually the solar panels on the International Space Station, and it's 3 little CubeSats that have just been launched from the International Space Station. And indeed, the CubeSat in the center was one developed at NASA Ames, really just a phone sat, kind of demonstrating that you can take one of these guys, which actually has more compute power and sensors in it than almost everything else that we've ever launched in space, and you know, demonstrate the capability in space. So we're really benefiting from the incredible technology development in consumer electronics and miniaturization. And I'm sure you guys, at least those of you in the Bay Area, have probably heard of Planet Labs, which is a private company doing Earth observation with a constellation of CubeSats. The guys that started Planet Labs actually were the original engineers that worked on this PhoneSat mission at NASA Ames. And so what do you get for all of this roughly $30 billion investment over the last 25 years? Well, this is NASA's prototype of the next generation of NOAA polar orbiting weather satellites, but this is imagery from an instrument that's a follow-on to one of the NASA imagers, follow-on to the MODIS, if you're familiar with that, the Moderate Resolution Imaging Spectrometer. This is one of the first global views of the Earth. But I really wanted to show a couple of images that talk to the kinds of sort of disaster response things that you might want this space perspective. So this was the Iceland volcano from several years ago. Oops. But you know, this gives you very quickly the kind of location and extent of the volcanic plume. This is the recent typhoon that struck Japan, and if it works at all, I'll show you a video of what we can do now with the new rainfall measuring missions, which are both a space-based radar as well as a microwave imager. And so we can really not only see the horizontal extent, but you can start to get vertical structure of these storms, which is a powerful diagnostic. And so one of the things that NASA is interested in is not really the operational weather forecasting, but really trying to understand the more detailed physics behind these systems, and can we diagnose why some of these storms grow into big monsters while some of them don't. And again, we actually just this summer, we're operating another hurricane mission in the Atlantic, this time again using robotic aircraft. This happens to be, I mean, this is an artist rendition, but this is the Global Hawk, which is another game-changing robotic aircraft that gives us 30-hour duration, whereas a conventional aircraft we can only fly for 8 to 10 hours. And so it's really opening up the measurement domain that we can use from aircraft. And then another interesting set of imagery is the lights from space at night. And I think these two examples are pretty striking and remarkable. You can see that one on the left is San Francisco Bay Area, and on the right is Washington, D.C. These images happen to have been taken by Don Pettit from the International Space Station with their own cameras that the astronauts carry. And so it's actually higher resolution than some of the night lights images that you'll see from space. But the really interesting thing about these images is that the night lights from space are really the only observation from space that's uniquely traceable to human activity. And indeed, you can just from looking at these images, you can diagnose policy and management decisions. For example, in the Bay Area, what you see is San Jose down to the lower right, San Francisco at the top there, but you can see where planners had the foresight to prevent development in the mountains that surround the Bay Area, and so they're dark. And then the other one in Washington, D.C., if you're familiar with Washington, D.C., it was laid out as a 10-mile on a side square turned on its side. And remarkably, you can see pretty sharply the boundaries of D.C. Compared to the surrounding communities. And that's simply based on the lighting policies and decisions that are made. So pretty remarkable imagery, just pretty remarkable information. And this actually has disaster response implications because in Katrina, the big tsunami that hit Japan, these lights go dark, and so you can see that very quickly. Another disaster response is wildfires. This is the view from space of the Southern California wildfires several years ago. Basically, NASA has an automated hotspot detection tool so that those red dots are showing where they're detecting fire hotspots. And then what we did at NASA Ames, but in collaboration with a number of other NASA centers, but also in collaboration with the Forest Service and CAL FIRE, is demonstrating a systems approach to how you would like to be able to respond to these wildfires and provide situational awareness. So I mean, basically what the firefighters see on the ground is that picture in the upper left, and if you can take that thermal infrared imagery with the instrument that we developed at Ames, and then do the onboard processing, do the distribution through satellite communication, and then web-based delivery, we're actually able to do in pretty much near real time with onboard processing. And we were sending data down directly to the incident command centers. This is one of the incident command centers back in those, I forget whether it was 2007 or 8. But what we were able to give to the firefighters are images like those in the upper right, where we used Google Earth, since the firefighters were used to that visualization tool. But we could show them where the hotspots were relative to the terrain, as well as where the fire fronts were moving. And so, unlike previously where they had infrared imagery, but they didn't see it until 6 or 8 hours later, we were giving that in near real time, and they were actually using that to make decisions to put boots on the ground. Interestingly, this is another little sideline. These kinds of command centers, they're kind of ubiquitous now. They're incident command centers, energy system monitoring systems. And actually, that's another area that NASA can claim some ownership in, that all of those trace back to the early Apollo days where we had the Mission Command Center controlling those human spaceflight missions. Another useful capability is the ability to monitor human activity, and particularly in this case, urban growth. Does everybody recognize what this is an image of? It's Las Vegas, Nevada, and Lake Mead there. This was circa mid-1980s. And then the next image is 2012. And if I'm careful, they're not quite registered, but not only can you see the explosive urban expansion, but if you look closely at Lake Mead, you see that it's actually gotten quite a bit smaller. And if I can get the technology tricks to work, I couldn't embed the URL into my PowerPoint for some reason, but I'll see if I can link to one. But this is a case, and I'll talk about this later, where the power of the long-term data records really, if you look at this in a time lapse over 20 years, it's remarkable what you can see in terms of urban expansion. And then just a couple of other examples of things that kind of are almost no-brainers in terms of the things that you can do. This is, again, looking at the recent polar orbiter, the the NASA precursor to the NOAA polar orbiters. But you can back out vegetation index, essentially a level of greenness, and you can quickly compare last year to this year in terms of the overall productivity in face of California's drought. And particularly in the Central Valley, you see quite a bit less greenness in the Central Valley. So one of the things I'd like to leave you with is that NASA really, I'd say, leads the world in terms of making their data public and readily available. In fact, I would suggest that we're actually putting pressure on other spacefaring countries to make much more of their data more publicly available. That's not universally accepted, but it's beginning to be more and more so. And then there are a number of organizations of spacefaring countries, the Committee on Earth Observation, Group on Earth Observations, who are making their own efforts to take certain amount of critical data and make that more readily available. So in NASA's case, we observe different aspects of the Earth system with different science focus areas or themes. And so what we've done, and this actually, interestingly, was developed before the days of the World Wide Web, actually, when NASA first implemented the Earth observing system in the late 80s, early 90s. And so we developed this, what we call the Distributed Active Archive System, or DAX. And they're basically data systems around the country that are thematically based. And you can go and get data from those DAX. In fact, I should remind myself before I forget. In fact, Cindy Schmidt also works with me at NASA Ames, but she brought a number of brochures that are back there. So if anybody's interested in following up on some of the things that I'm talking about the data systems or the other systems that we're talking about, we have some flyers back there. So there are a number of efforts. This is not trivial. You know, one of the challenges is these are massive data sets, and it takes an incredible amount of data storage and computing power to be able to actually do anything useful. And so NASA has made a concerted effort. I mean, they've been managing the DAX for quite a long time, since the mid-90s, I believe. But there's a new effort called Worldview, which really attempts to make the data much more readily accessible in a map-based tool. So you can go in and look at near real-time satellite data on Worldview, and then you can select different parameters or different locations, and you can pull up maps based on that. You can actually either grab a frame and do a snapshot, or you can actually download the data from that map. And this just talks a little bit more about the kinds of things that you can do. Again, I think there may be some brochures back there on Worldview, but it gives you the URL, and it kind of goes through. And indeed, on the website, there are some tutorials for how you use Worldview. Another effort, which again, as I mentioned early on, we have the Applied Science program. This was an applied program that was a competed research project. It's now an ongoing program, actually led by Dan Irwin at NASA Marshall in Huntsville, Alabama. But it's become a very strong partnership with USAID, and it's basically looking to take NASA data sets and really get them out internationally in developing countries where they don't necessarily have the capacity to come to the DAX and really use the data sets. And so what started as a Central American effort for the original Severe server then expanded to Africa, and now is in India and the green shaded part of the world. The actual data server system is in Kathmandu in Nepal. And then as it says, they're coming in 2015 as a data center in Southeast Asia. Again, there are brochures for Severe in the back there if you'd like. And this is where I was going to try to get out of PowerPoint and see if I could bring up a web page. But I think it's interesting. I mean, NASA is making a concerted effort to make the data much more accessible. But interestingly, there are various commercial efforts to do the same thing. Some of them are pay for service, but in the case of Google Earth Engine, they basically make this kind of capability. They try to do with Earth data analysis what they've already done with map data in Google Maps and Google Earth. And so bear with me for a second. See if I can get out of this, bring up my browser. Yeah, so this is actually just one of their examples on the front page of Google Earth, but this is that same view of Las Vegas, Nevada, and it starts, the nice thing about what Google Earth Engine can do very quickly is show you a time lapse. They have made a concerted effort to get the 40-year archive of Landsat data from the USGS that manages that data, and they have that now readily available in this Google Earth Engine. So just another nice example of, one thing that's you kind of lose track of is that when NASA first started launching these satellites, if we could analyze one tile of Landsat data, we thought we were doing pretty good. But now with, one of the big changes is, of course, based on Moore's law, and the ability to have a tremendously more compute power now. And so that actually dovetails into my next topic. How am I doing on time? Okay, I'm going to wrap up real quick. So this is an effort actually led by a real innovator at NASA Ames, Dr. Rama Namani, but basically taking advantage of that idea of Moore's law. NASA Ames has a supercomputer lead for the agency, and so this is a partnership between the Earth Science Division at NASA Ames and the supercomputing, but creating this NASA Earth Exchange, or NEX, which is, really rather than, so with Moore's law, compute power has gone up, data storage has gone down, and the one thing that hasn't really kept up is the bandwidth to move all of that data. So rather than everybody downlinking that data and processing it on their own systems, Rama's vision was to basically create an environment where you brought all of that capability together. All of the NASA Earth observation data sets on spinning disk, we're making a pretty good dent in that we've got all of the Landsat data, a lot of the other Earth observation data. But bringing that into a system with a social networking front end where people can actually access the data, the open source models, the analytical tools, and be able to work together with workflow management, so people can also not only store their final results, but the complete workflow that went into that. And other people that come in and use the system can basically take advantage of those previous workflows. Okay, there are a number of applications. We're looking at using this system to forecast water demand in the Central Valley, to really look at, can you increase the efficiency of irrigation in California, a $45 billion industry in the state. But and we've also recently developed a partnership with Amazon Web Services. So we've got a version of NEX running on the Amazon cloud, which actually makes it much more publicly accessible. But I wanted to leave you with just the thought that, and the excitement of the work that we do, actually. So one of my bosses at Ames, who was an engineer and came to work in our science organization, made the comment that, most of the people that work in the agency, they actually see that as their job, whereas you came to the science organization and those people tend to see this as their life. And so one of the things I wanted to leave you with is the other thing that Rama is currently doing, and it's more in the spirit of this conference, which is he's from a farming community in India, and so he's actually going over there on his own time, doing leave without pay, and working with the government of India, insurance companies, and actually Swiss Re, which does a lot of the reinsurance for the agriculture business in India, and really trying to instill some of these quantitative analyses so that when farmers have a crop failure, you actually have a quantitative look at what really caused that, and are therefore better able to get the insurance if the crop failure was not the farmer's fault. So fundamentally changing, modest ambition to fundamentally change the way agricultural insurance is done in India. And that's it. So thank you very much.
What's our fugitive methane detection capability now and in the future?
Well, we actually, the Japanese have a satellite called GOSAT, which is doing column measurement of both CO2 and methane. It's got a pretty broad spatial resolution. I haven't actually worked with the data, so I'm not too familiar with it, but it's a way to get sort of global distribution of methane. But we have a number of other instruments that do in situ measurements of methane. And so, for example, we have a partnership at Ames where we're doing greenhouse gas measurements around California and measuring methane. And actually, we're using a commercial instrument that's actually homegrown here in the Bay Area from Picaro Systems. And I know Picaro is actually, they're spending their own resources to do a lot of methane measurements around fracking areas and drilling areas. So and some of those measurements suggest that the amount of leakage from some of these fracking sites is significantly greater than people estimate currently.
All right, we have time for one more question if anybody has one. You got your hand up first.
Thank you. NASA Ames was doing a lot of sort of open source conferencing and things like that. Are you still doing that, inviting conferences and people to interact with them?
Yeah, actually, that's one of the strengths that we leverage with NEX is that for about 10 years, Ames has built these virtual institutes. It started with the NASA Astrobiology Institute, where it's basically literally a global virtual institute, and so most of the work gets done virtually with virtual conferences and working meetings and things. And so that's a lot of what we've put into NEX is that capability to do, to keep that global group of collaborators together and interact.
Great. Well, I want to thank Steve very much for closing us out. And the other thing I wanted to mention is we got a large grant from NASA to put this conference on. So this conference would not be possible without NASA. So on behalf of NASA, thank you very, very much.
I wish I made all the financial decisions.
And here is a gift of, you are going to get one of those, definitely, because they are the coolest.
Thank you very much.
Yeah, thank you. All right. So I wanted to say, I wanted to thank every one of you for coming. This has been a fabulous weekend. I enjoyed meeting so many of you and hearing your comments. And this is pretty much the end of our conference, but gosh, I sort of forgot what I wanted to say. Just thank you all for your participation. I hope you had a good time here. I hope that you will continue to involve yourselves. And we do have a big feedback form, and Joe is going to show you that. But before we close up, I would like to bring up for just a few minutes our chair for next year, who is Joe DeCure. He has a couple of slides for you all. And it's been my honor and my pleasure to be here, and thank you all so much.